We've now seen the method of substitution through an example or two. What we'd like to do now is formalize the process. If you're going to try the method of substitution, and again, keep in mind for integration, there is a trial and error element to it. You do have to try something, see if it works, and if it doesn't work, try to identify why, and see if you can improve your method or choose a different method that's more appropriate. Once you've decided you're going to try a substitution, the first thing you have to decide is what you're going to call this new variable, this variable that was not in the problem to start with. Usually what you're looking for is the derivative of whatever you're picking to be in the integrand as a multiplier as well. Step 2 is find the derivative, dw dx, assuming those are the variables, and then solve for the dx part, because in our integral that we start with, there is a dx that we need to replace. So we want to isolate dx, and then we'll have something to replace it with that has w's in it. Last but not least, we rewrite the integral with only w's and dw's, making sure there are no x's left over. You can't mix your variables for integrals, just like you cannot mix variables for derivatives. And if you've done the right step or have made a wise choice, you should be able to evaluate the integral. And that means the substitution was effective. Do the integral, work your way back. If it turns out you couldn't get rid of all the x's, or you got a new integral that was actually harder than the one you started with, then that points to the need to try something else, some other alternative method, and we're going to see a couple later on in the course as well. But substitution is usually the first go-to method because it's fairly straightforward to execute, and usually there's some signs that it might be beneficial in the form of the integrand you see to start with. As our next example, let's find the integral of tan of x. Now, one thing might be to try a substitution with w equals tan of x. Just replace this with our new variable thing w. That doesn't seem like it's going to be too helpful though, because we don't see the derivative. There's no secant squared of x, which is the derivative of w, in the integrand. So maybe that's not going to help too much. What is often required in an integral is to rewrite what you started with into a form that might be more amenable to integration. And in that, for this case here, I mean rewriting tan as the ratio of sine over cos. Now this has some promise, because we know sine of x is the derivative of cos essentially, and the derivative of cos is sine, again with some minus signs, but certainly the family of functions is correct. For this, remember we want two things. We want to be able to pick an inside function. In this case here we could pick sine or cos. But we also want to have the derivative as a factor. If I pick cos of x as the w, sine of x is a multiplier. If I pick the other way around and pick sine of x as my w, then I'd be dividing by cos. Cos wouldn't be a factor. Cos would be a 1 over or a divisor. It's a little bit different. Again, practice is the best way to get a feel for these kinds of things, and it is a bit of an art. But in this case here, we're going to pick cos of x as our substitution, and then we're going to follow the process we just outlined, which is then compute the derivative. The derivative of cosine is negative sine of x. Here's where it's very important to keep your integrals versus derivatives separate. The derivative of cos is negative sine, and that means if we bring up the dx, and we're going to bring down the negative sine, we'll have negative 1 over sine of x. The dw is still there, so we're literally just moving pieces around in an equation. That equals dx. And again, look at what's happening as we do that. We're going to replace the dx here with this expression, and that is going to be dividing by the derivative of our w. And that's going to be super handy for us, because when we rewrite our equation, the sine of x stays as is. The cos of x is what we call w, so we're going to rename that w. And then the dx here can be replaced by this expression, negative 1 over sine of x dw. Doesn't look too nice at first until we recognize we have that cancellation. The two signs cancel, and we end up with negative the integral of 1 over w dw. Perfect. This is a new integral, and that new integral is all w's, more explicitly no x's, so check, and it is simpler. Check. So we've made some major strides here, turning the integral of tan of x, staring at that for hours, no idea what to do, and trading it in for the integral of 1 over w. And this, again, think about what you have to differentiate to get 1 over w. Think back for a moment. Remember, it'll be ln. And we also have that one tweak, because it's possible w could be negative. We get this ln of w in absolute value as our antiderivative. When we do this, we're going to get negative ln absolute value of w plus a constant. And we're almost done. We just have to go back to x's. The question was, what's the integral of tan of x? It doesn't make a whole lot of sense to say the ln of w is that. So we just go back. Our w was cosine of x, so we'll have the absolute value of cosine of x plus a constant. And that, we think, is our integral. Though it isn't actually required unless we ask for it. If you're writing a test or an exam and you have 2 or 3 minutes to spare, it is really worthwhile checking your answer because it is so easy. Remember, all you do to check an answer is take the derivative. We were told to take the derivative of, sorry, let's go back a step. We were integrating tan of x, and we claimed that this was the antiderivative. If that's true, we should be able to differentiate this and get tan of x back. That should be the loop. So let's differentiate that and see what we get. We have negative. The derivative of ln of anything, even the absolute values, is 1 over that same thing. Then we multiply from the chain rule the derivative of the inside. Derivative of cos is negative sine, and the derivative of the constant is 0. Notice we have a double negative, so it goes positive. And we end up with sine of x over cos of x, which, as our favorite simplification, is equal to tan of x. That equals our original integrand. And so we have the right antiderivative up there.